All right, so in the last video, we looked at the even and odd identities for some trigonometric functions, for all 6 trigonometric functions. And we focused pretty heavily on what that implies as far as symmetry for the graphs of those functions. But we actually haven't even looked at the graphs of our trigonometric functions. That's what we do in Chapter 8. Right now, our ability to use those even and odd identities is somewhat limited. So here's a case where they are helpful. I want to use the even and odd identities to evaluate a couple of trig functions. Now, both of these functions, we can find the exact values of these without using these identities. We would just sketch the unit circle, find the reference angle for each one of these. They both turn out to be special angles, and then we can use our unit circle to determine what those are equal to. However, the even and odd identities just makes this go a little bit faster. So here's what I mean. If I want to evaluate cosine of negative 45 degrees, cosine turned out to be an even function. So because it's even, remember, even functions will sort of eat up these negatives. It'll absorb this negative, which to us means that cosine of negative 45 is the same thing as cosine of positive 45. That's literally what the even identity tells us is true about this. If I plug in an input and its opposite both into the cosine function, the result should be the same. These should be equal. Now, the benefit of this is that cosine of 45 degrees is something that you should have memorized by now. The cosine of 45 degrees is root 2 over 2. So I didn't need reference angles. I didn't need to draw a unit circle. I could just use what I know about the cosine of those special angles in the first quadrant to make this determination. Let's do something similar with the cosecant function here. Cosecant of negative pi over 3 is what we're asked to find. And from our even and odd identities, we saw that the cosecant function is odd. That tells me that negatives can be brought out. They don't disappear like they did up here. For odd functions, you bring them out of the function. So this becomes negative cosecant pi over 3. Now, keep the negative there. Cosecant is not one of those functions where you memorize a bunch of values for typically. But that's because we opt to rewrite it in terms of 1 over sine. What is negative 1 over sine of pi over 3? Well, this would be negative 1, let's write this, negative 1 over root 3 over 2. And again, this root 3 over 2 comes from my knowledge of the unit circle. I know that sine of pi over 3 is equal to root 3 over 2 just because I've memorized the unit circle, which you really need to do. 1 over any number is the same thing as taking the reciprocal of that number. So this is negative 2 over root 3, or after rationalizing, negative 2 root 3 over 3. Okay, feels like that one took a lot more work, and that's just because we were working with a cosecant instead of a cosine, and we had some rationalizing to do. But if you think about it, this is still much more efficient than having to draw the unit circle and find reference angles, which would still work. It's just more cumbersome. Okay, let's go ahead and move on. So what we're going to be doing in this example is showing how trigonometric identities, things that we've established previously, can help simplify expressions that involve trig functions and may be potentially somewhat complicated. Now, we do a whole lot more of this kind of thing in Chapter 9. That's where we deal the most heavily with trig identities. But here is sort of a preview to that. So the goal here, it says, is to simplify this expression. It's tangent of t over secant of t times sine of t. How do we do that? Well, generally what you want to do in these types of simplifying problems is convert everything into sines and cosines. Remember, all of the trig functions can be related back to sine and cosine somehow. So I know that tangent of t, let's rewrite this, tangent of t over secant of t times sine of t. Tangent of t is the same thing as sine of t over cosine of t. That's one of the identities that we've established. Secant of t is the same thing as 1 over cosine of t. And then this whole thing is being multiplied by sine of t. Now notice the cosine of t showing up in the denominators here and here. those cancel out. And what I'm left with is sine of t over 1, or just sine of t, times another sine of t. That's sine squared of t. Okay? So this is arguably simpler looking, easier to work with than this original trigonometric function, or not function, trigonometric expression, in the sense that it only involves one trig function, where this one involves 3 different trig functions. So what we've established, though, is that these two expressions are in fact identical. Any number I plug in for t in this expression will give me the same thing if I plugged it in over here for this expression. So that simplification can be really useful in applications. On the topic of identities, I want to return to our Pythagorean identity. Remember, the Pythagorean identity was cosine squared of t plus sine squared of t equals 1. We established that in the last section, and I did mention back then it's probably the most important identity that we encounter. And I think I also mentioned in that section that there are 2 alternative versions of it involving the other trig functions. The way we get those other versions is we recognize that this identity is an equation, as all identities are, and equations you can perform algebraic manipulations on. I can divide both sides of this equation by the same non-zero number if I wish to. So let's suppose that I divided both sides of this equation by cosine squared. That's what's happening right here. Okay, dividing everything by cosine squared. Well, cosine squared over cosine squared is 1, because I'm dividing something by itself. Sine over cosine is tangent, so it follows that sine squared over cosine squared would be tangent squared. And then finally, 1 over cosine squared, that's the reciprocal of cosine squared, which is secant squared. That gives me 1 plus tangent squared of t equals secant squared of t. And this is an alternative version of the Pythagorean identity. It's something that can be used in place of this one if we needed to. Alternatively, over here I divided by cosine squared. If I divided everything by sine squared of t, and then simplify in a similar way, I end up with this third version of the Pythagorean identity. Cotangent squared of t plus 1 equals cosecant squared of t. Okay, and that's where these 2 alternative forms of the Pythagorean identity come from. Okay, so let's see. Let's try doing an example where it might be helpful to use one of those trigonometric identities. Let's see. Let me scroll down a little bit. There we go. We're given some angle theta, and we're told the value of 2 out of 6 of our trig functions for that angle. Cosine of theta equals negative 7/10. Tangent of theta equals negative root 51 over 7. Okay, and we're asked to find the other 4 trigonometric functions evaluated at theta. Now, there's a couple of things